A standard linear spring has a Hooke's law relationship that describes how much force is required as you change the length of the spring. That's what this says. And I need to impress upon you that if I have just any old spring that is linear, I haven't even had a chance to really talk about the difference between real and ideal springs. So we'll just assume we're dealing with an ideal spring. If I want to compress the spring, I'm not even talking about putting a box there. I just walk up to it and I push on the spring and apply a force. While the spring is uncompressed, it requires zero force to just touch it. But if I want to start to push on it, the more I start to displace it, the harder I have to press. Does everybody understand that idea? You did this. You had a spring that was hung on a little hook, and you put weights on it. Do you remember doing this? You have data that you haven't done anything with. And as you added more weight to it, the spring stretched more. So this is not bizarre, right? You can imagine this. Now, the reason I bring it up is it's not like there's one force that compresses it up to 10 centimeters, and then the next force compresses it the next 20 centimeters. For every small change in position, the force is forever increasing. It's linear, meaning I could plot force and displacement, or more importantly, I could plot force and position. The F is what I push. The position is the position of that plunger. So I'll say that the plunger starts at 0. If I push it in a distance, well, let's just say X, it will take a certain amount of force to do so at X. But it's linear. And what I mean by it being linear is that the relationship between how much I have to push on the spring and how much it's displaced goes up a little bit with every change in displacement. Is there any question about that yet? Are we sure? So you can follow along that right now, just holding the spring at X requires whatever this amount of force is. And if I want to push it in just a little bit more, as I move from X1 to X2, is an ever increasing amount of force to get there, so that now I'm at X2 and I'm holding it with this amount of force. Everybody good so far? Well, if I wanted to calculate how much work it takes to compress that spring, I cannot use this definition of work. Because for each small change in X, the force doesn't stay the same. The force increases. The force is never constant. as I try to push the spring in. It's always an ever-increasing amount of force required to make changes to the length of the spring. Does everybody understand that to this point? Are we sure? Because this is where it's going to transition, and we're going to try and figure out how we could come up with the amount of work done without using F times delta X. Are we sure? Because it's going to get harder from here. Okay. Well, one way to do so would be to recognize I have a clear function and a graph that supports that function. And because I have a clear function and a graph that supports that function, I can recall that looking at a functional relationship on a graph gives me data and properties that perhaps could be exploited to figure out the work done. Remember, whenever I have a graph, I can check to see what the meaning of the slope of that graph and the area of that graph might be. So when I look at this graph, it looks to me like the area of this graph could be the work done. It would be the force times a change in position. You guys see that? Are we sure? Because if you don't understand this part, there's no point in going further. All right, so I'm not going to use this. I'm going to say to the class that we can find the area here. Part of the reason we can find the area is we have the relationship. Now, this part might seem a little esoteric to you, but let's imagine that we have a spring with spring constant K that at its rest position is at 0. And I am going to compress it to a position X final. This corresponds to an ever-increasing but maximum amount of force we'll call force final. Now, to compress the spring, the force is going to start from 0, because it takes 0 force to hold the spring at 0 position, and will increase to some maximum amount for the force over a distance of X final. Is that all good for everybody? The work done will be the area under the curve. Which I think looks remarkably like a triangle. Would you agree? We all good with that? So the area under the triangle would be 1/2 times force final times X final. We all okay so far? I don't know if you guys can see what I'm about to do here, so I'm going to try. Force final has to equal K, stripping away the negative sign because that only has to deal with direction. And it just says that the force from the spring is in the opposite direction of the displacement. But we're pushing in the direction of the displacement, right? This is the work we do on the spring, which is why I'm leaving the negative sign out. We're all okay with that. Go ahead.
So for you said that when you push into the position, so K no longer be negative?
What I'm saying is that this relationship is about the spring. And it says that if I displace the spring to the right, the spring pushes back to the left. That's why the negative sign here is in Hooke's law, because Hooke's law is describing what the spring does. but I am the one pushing on the spring, and I am pushing in the direction I am displacing the spring, which is why I'm going to make it positive for the force I applied. Is that okay?
Yeah.
Are we sure?
Yes.
Awesome. And this is going to be, the delta x will be x final minus 0 because we started when the spring was not displaced at all. We all okay so far? Well, I'm going to do substitution. I'm going to substitute this over here. And I'll find the work done compressing the spring is 1/2 times, well, let's put that in there, k times x final minus 0 times x final. Well, this is not meant to be a surprise. This is meant to be an obvious answer. And when we're looking at our answer, I hope you notice x final minus 0 is just x final. So this whole thing becomes 1/2 k x final squared, which should not be a surprise, even a little bit. It's the elastic potential energy in a spring. Did we follow this argument okay? Because this is not at all what the integral is about, but it's also everything that the integral is about. But this was just basic geometry and the application of the idea of area under the curve. Are we good to keep going? Okay. Slide that over there a little bit. I'm not going to explain to you why calculus works the way it does. I can't, I don't have the time. What I'm going to say to you is that the integral finds the area under the curve. It's a sum of all of the areas that you get in the curve. What calculus technically is doing is taking this particular relationship and breaking it up into small areas. Looking at just a small change in your function. In calculus lingo, we name that small change dx, not delta x, to indicate it's a small change in position. And when we are given a definition that has the integral symbol in it, like this one, it's telling you to look at your function for force. I'm talking very slowly here. If you need me to slow down so you can write things down, I am all okay with that. But it says, look at your function for force. Does it change as your position changes? If it does, then let's find out what this product is for the smallest possible change we can accomplish. In fact, we're going to take this and break it up into as many small changes as we can realistically do. And calculus says that there's an infinite number of these small changes. Now we'll look at the smallest possible change in displacement so that the force can't possibly change very much over that displacement. Do you understand what I mean by that? We're talking about if you make the change small enough, does the force change very much? You can see in this picture, no, it wouldn't. If I can get those two lines close enough together, the distance between this is going to be just a dot, right? It's going to be a small, 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 small change. The magic of calculus, and I say it's magic because it does feel that way. But the magic of calculus is that if you just do the process as I've described it to you, it will do this sum. It will find this area. Because this symbol then says to take every slice that you've made and add them all up from where you say to start to where you say to finish. That's what it says to do. And you don't have to draw a graph. It doesn't even have to look that pretty. It can be any function. Any function will work if you just follow the procedure. Now, our function was an easy one because it was a triangle, so we could see the area. But we're going to do another example directly after this where it's not like that at all, just to prove it. Now, an integral itself is a process, but it is a sum. It's adding up all of those slices, every little bit. It's saying, take one small delta x, multiply by whatever the force is for that delta x, and then go to the next one, and then go to the next one. And then when you're done, add them all up. But we're not going to actually do any adding, and we're not ever going to actually multiply any two things together. What we're going to do is take the integral, which is a two-step process. Find the antiderivative. Apply the limits. All right? Two-step process. So let's set up our integral. We do have to set it up. First, we are asked to find an expression for force that matches our object. We already have our expression. Our expression is kx. That's our expression. I don't have to use delta here. I'm using kx and not delta x on purpose because we have a thing where we're going so close together that the delta is super, super small. It's just an x. It's a location. This is still our dot product. That's because it's part of our definition of work. That's not part of an integral. That's just a definition of work. It just tells us we have to take into account the direction of the force and the displacement. We've handled that. We're pushing to the right, and the spring is going to the right. That has nothing to do with integrating. The only way we would have to worry about that is if the angle changes as we move. Then we would have to take the angle into account. But the angle is always going to be the same for this, isn't it? It's always going to be cosine of 0 degrees. So I'm not going to worry about the angle for this one. So then I write delta x here because there's nothing left. Now I'm just setting this up. That's all I'm doing. I'm setting this up. So I put in my function. I checked about direction. I put in dx. Now I got to tell it, where am I starting from and where am I going to? The bottom is where we start from, 0. The top is where I'm going to, x final. Trying to find out the work done in compressing the spring. Yep.
So what's kx again?
Hooke's law. Right there. Hooke's law. Hooke's law. That's how springs work.
Yeah.
We're good?
Yep.
Okay. All right. Now, the summation symbol tells you are taking the integral. Dx tells you which variable is the important one. Everything in the middle is the integrand. This is symbology, meaning these are the symbols calculus uses to communicate to you what it's asking you to take the integral of. The integrand, this part, is the part where we find the antiderivative. Now, there are things you can do to make this part easier on you. For example, every single term in this sum is going to be multiplied by k. So it is not a problem if you have a constant to recognize that the constant will be in every term, and you can pull the constant out front of the symbol because it's the same as a summation. If this were a summation of k x I from I equals 1 to some future number, every single sum would have a kx in it. I could pull the k part out. It's not changing with each piece. If that's your hand up, you're going to have to do better than that. I am a blind person. Put them up there and say it.
If I were to put F final instead of X final, would that be a problem? 'Cause F final is not necessarily the position of it.
Yes, you would have a problem. We need a function that has something to do with x in order to take the integral with respect to x. Yes?
Why are we pulling k out?
Because we can. Does k change at all for any of the x's? So whether I push the spring in a little bit or a lot, is the value of k ever different? No, because the spring never changes. This makes our integrand as simple as possible for doing the antiderivative. Does that make sense?
Yeah.
I don't actually have to pull it out. There's rules in calculus to how to deal with stuff like that. But if you can, I think for your sake, it might be easier. Is that all right?
Yeah.
Excellent. Okay. Now here's the part that, is the magic. And I say that because it is, I'm not even going to tell you where it comes from. Because I don't remember how to deal with the fundamental theorem of calculus. Because once you learn it the first time, you never go back to it. And you guys are in AB, you learned the fundamental theorem of calculus by now. It's the definition of where derivative comes from. But I don't know how many times have you used it. It's got limits in it on the top and bottom, and it's got like limit of something plus some, I don't even care to remember. But once you learn these processes, you just do it. We're going to find the antiderivative here, and you do have to recognize what your function is. For example, this is a polynomial. A polynomial is just a variable to a power. But if it was, say, sine of x, well, I'd have to have a different thing to do. I would need to know what the antiderivative of sine of x is. And if it was e to the x, I'd have to have something else there. Every single function possibly has its own antiderivative, which is why they provide you a table of antiderivatives on your equation sheet. But you guys who are in calculus are going to build your own internal list of antiderivatives. I have only taught you one antiderivative, and it is the polynomial function, because it's the only one that we use a lot. We will use three. You just saw them. The polynomial, the trig functions, and the exponential. The only ones you will have to know. And the antiderivative of a polynomial, x to the n, with respect to x. The antiderivative is add 1 to the polynomial and divide by the new exponent. Sorry, add 1 to the exponent and divide by the new exponent. This is not new. We did this in September. It should be in your notes. You should be able to find them. I said, make a special section of your notes about how to do this, because it will come up. It has come up. We are using it. Now, I will point out that there doesn't appear to be an exponent on the x, but there is, isn't there? What is the exponent on the x? 1. So I'm going to perform the antiderivative, step 1. The first person to ask where the 2 comes from loses an eye. I'm going to add 1 to the exponent, which is currently 1, which is going to make it x squared. And I'm going to divide by the new exponent, which is dividing by 1 plus 1, which is 2. I've done it. I have found the antiderivative. Now, that process ultimately gets rid of the summation symbol and the dx. That was just there to remind me that you're taking the integral, you're going to find the antiderivative. And look, sometimes the antiderivative is harder, it's more complicated. This one, not particularly. But we're not done. There's still the k that we brought out front. And I still have to apply my limit. So I put this bar here. And if you're in calculus, sometimes they want a bracket there. It's just a reminder, a way to remind you that you have to apply your limits. And this still equals work. Now, somehow this magically created a function that will tell us the area. And yes, it's magic. And no, I don't know how it works. Yes, I do, but I don't want to talk about it. Just assume that it's special calculus magic. Now, I do have to apply the limits, and I don't want you to forget stuff like that. Applying the limits is important, but in this case, applying the limits just means put in the top limit for your variable first. So k x final squared over 2, then subtract and put in the bottom limit for your variable next, k times 0 squared over 2. And then you're done. Now, you might want to rewrite it so it looks nicer or something, or get rid of the things that have 0 in it. But this is the work done in compressing a spring. It's not a surprise. We already did it using algebra. But this is how you find the work done in compressing a spring using calculus. Yes, Andrew.
So where did you get the negative k 0 squared over 2?
Much worthy of an answer, and I don't know why that happened, but let me start by telling you, you are right to be concerned about when would you know to do this. So let me give you the simplest examples or things you can figure out that would help you figure out when to do this, okay? So it's not going to be obvious. So, and this is going to take a second to come back. There are only 2 instances right now where you might have to do this. The first, as we've come up to understand, is that if we're dealing with motion equations, in which the acceleration isn't constant, then we have need to do something like this. That was the first instance that we had this year of when we might need to do this. In the case of this problem, our definition of work has the integral symbol in it, which suggests that anytime we're calculating work, it might be an integral. But truthfully, the only time we have to integrate is if our force is not constant throughout the displacement. If the force is not constant throughout the displacement, then you have to use this, or you have to graph it, or you have to do something else. Does that make sense?
Yeah.
Okay. Go ahead.
So if it gives you a graph, you find the area under, and that's basically doing an integral with the graph. And
That
if
is
it doesn't give you a graph, you do the steps you just showed us.
Yes, that is exactly the right way to go. If they give you a graph, if you can find its area, that'll probably be easier because it's probably just doing simple geometry. But if it doesn't, you have to use this. So here's the most common counterexample to a spring problem. It's in the exam frequently, or used to be, so now they don't ask it very much. but it's a non-linear spring. And whenever they picture a non-linear spring, they always picture something kind of silly, like something like this. A non-linear spring is a spring in which the force isn't uniform, doesn't uniformly change. The most common example is a spring that is like this, minus kx cubed. This is a spring that doesn't just increase the amount of force required to compress it, but increases it a lot, because if you just compress the spring a little bit, the amount of force goes up by the cube of the displacement. Does that make sense? And are there springs like this? Yes, lots of them. Most people who drive a vehicle have linear springs, but if you have a vehicle that like is made to carry loads, it has helper springs built on. Those helper springs don't kick in until you've actually compressed it a little bit. They act like this. There are lots of situations in which a linear spring just isn't enough. You need to have something that requires more energy and ramps that energy up if you're starting to compress it too much. And you can see how in a truck, if you give it a lot of load, you don't want it to bottom out. But like for everyday driving, you don't want the springs to be too stiff. So what trucks do is they have a nonlinear spring system that makes it so that under no load, your car drives okay, and under lots of load, it still drives okay, because the springs get more powerful as you get more weight in the truck. It's just an easy way to make your car a little bit easier to drive. So they will use nonlinear springs. Now, a nonlinear spring looks like this. I mean, they are like that. You get more powerful as you compress them. So as you compress this a little bit, it takes a little bit of force, but a lot of force starts to increase quickly because it's x cubed. The most likely two examples will be an x cubed spring or an x squared spring. Now, this one is an example where even if you plotted it, you'd be unlikely to be able to find the area of that plot, because if this is position and this is force, x cubed looks somewhat like an x squared if there's no, other terms to give that little funky, humps and stuff in it. You guys know what I'm talking about? So it's harder to find this area because, again, it's not linear. That's not a triangle. But if we still say that we're going to compress the spring to say something x final, we can calculate the work. The work's going to be the same process we did before, which starts with us realizing we are going to compress the spring, even if it's nonlinear, from its rest position to some compressed position. And this isn't going to be that weird. We're going to do the same thing. Notice I set everything up exactly the same. And all the same arguments can be made. This is the force from the spring, so I made it positive because I'm going to push in the direction of the spring, and it's going to go in the direction I push. Everybody okay so far? The process is still the same. I'm going to find the antiderivative. I have a function that is based on position. I'm going to pull out the constant to make it easier. I'm going to, step 1, find the antiderivative of my integrand. Well, that's x cubed. So the antiderivative of my integrand requires I take the 3 and add 1 to it, and then divide by the new exponent. There, I have found the antiderivative. My next step is to put in my limits of integration. And that will be x final to the 4th over 4 minus 0 to the 4th over 4. Now I'll do whatever arithmetic is necessary to put it together in a term that works. The amount of work done. It looks something like that. And you don't know if that's right because you don't have experience doing this. And I can get how scary that must be. And it's not like you can go back and fill in that area and see if that's the right area. I get that. But that's supposed to be the actual beauty of calculus, is that this works. It might seem like voodoo, but this is the area under that curve. If you were to fill it in and color it in red, that's how much color stuff it would take. It is the area under that curve. Yeah. We went off the rails a bit on Friday doing this, but I want to impress upon you what we had. If you remember what we had, we had L minus X times M over L G dx evaluated from 0 to L. Do you remember that? Please, just to humor me, try this again now after having today's lesson and see what happens. Please?